So today's lesson is on residuals. Residuals calculate the predicted value minus the actual value and tell us how far away that our line of best fit is from the actual data that has been collected. And it can be used to determine if a linear function really is the best fit for a set of data. So let's take a look at example number 1. A skydiver jumps from an airplane and an attached microcomputer records the time and speed of the diver for the first 12 seconds of the diver's free fall. The data is shown in the table below. Part A, we want to find the equation of the line of best fit for the data set, rounding both coefficients to the nearest tenth, as well as determining the correlation coefficient and rounding it to the nearest hundredth. Then, based on the correlation coefficient, we're going to characterize the fit as positive or negative and show how strong it is. And last, we're going to create a plot with both the data and the line of best fit shown on our calculator. So to do that, we want to go into Stat, over to Edit, and we want to enter in the points that are in the table, with time being our x-axis and speed being our y. So time is our L1 and speed is our L2. So you can see that I've already done that. So if you need to, you can pause the video here and go ahead and enter in all of that. Okay, now that you're back, we want to make sure that we have some things set up so that we get the correlation coefficient as well as just the equation. So remember, in order to get the correlation coefficient, we have to have our diagnostic on. You probably already have that set up from the last time, but just in case, let's make sure we go to second and 0 for catalog, scroll all the way down to diagnostic on. Once you get to diagnostic on, press enter and enter again, and now you're set up. So remember that you need to know how to do that, because on the day of the regions, you're going to clear your calculator and you have to turn that back on so you have this feature ready to go. All right, so now that we're here and we have our list L1 and L2 set up, we can go to Stat, we can go to Calc, and we can choose choice 4 for Lin Reg, enter all the way through. And now we have our equation and our R value. So our equation for this line of best fit is going to be y equals, remember they want to the nearest tenth, so 6.0x plus 13.1. There's our equation of the line of best fit. And then our R value, rounded to the nearest hundredth, is 9 or 0.94. So how can we characterize this? We can characterize this line as being a strong positive relationship. Strong because 0.94 is really close to 1, and positive because 0.94 is positive, and also because the slope is positive. So now we want to graph that and show that that all works. So to do that, we're going to go to our y equals. We're going to put in our equation. So we're just going to do 6x. We don't have to put 6.0 plus 13.1. Oh, and I forgot my plus sign, so I'm going to go to second insert and plus. And then we're going to choose zoom and 9 for zoom stat. And there we have our line of best fit through the data. So notice that data kind of has like some curvature to it. So you might be noticing right away that, maybe a linear function isn't the line of best fit here. So let's go through and do the next part. So B says, the residual of a data point is defined as the difference between the observed y value and the predicted y value. So the actual y value minus the predicted y value that is calculated by the line of best fit. Calculate the residuals and place them in the table below with the predicted values rounded to the nearest integer and the residuals for each data point. So now what we're going to do is actually find the prediction. So now that we have the line of best fit, I can go to second and table, and from my equation, it has generated all the predicted values, the points that would be predicted based on our line of best fit. So for 0, we actually would have a prediction of 13.1. So let's make that just 13 because it says rounded to the nearest integer. For 2, we would have a prediction of 25. Look, spot on right there. For 4, we would have a prediction of 37. For 6, we would have a prediction of 49. For 8, we would have a prediction of 61. For 10, a prediction of 73. And for 12, a prediction of 85. So now our residuals would be the actual minus the predicted. But our calculator will actually even do that part for us. So we can again go to second, or not second, just stat, go to edit, and we're going to change L3 to calculator residuals. Go up to L3, go to second and list, change it to 7 for resid, and press enter. And all of our residuals will be there. So if I actually wanted to calculate the residual, I would do 0 minus 13, and I get negative 13. And our first value is negative 13 if we were to round it to the nearest integer. For our second residual, we do 25 minus 25 and get 0. And our second residual, if we were to round to the nearest integer, would be 0. The next one, if I were to subtract 46 minus 37, I would get 9. And in the table, the residual is about 9. For the next one, 60 minus 49 is 11. And in the table, 10.7 will be rounded to 11. Then the next one, 68 minus 61, is about 7, or exactly 7, which in the table it would be about 7. 72 minus 73 is 1, and negative 1.4 would stay as negative 1. Actually, negative 1, not 1. And then 74 minus 85 is negative 11, which is shown also in the table. Actually, in the table, I think it looks like more like 12 it would be rounded to, but if we go by our predictions, we're just going to leave that as negative 11. So now it says to sketch a plot of the residuals shown below. Do the residuals show any distinct pattern? So I'm just going to leave those there on my calculator and graph what I see. So this is now our x-axis, and this is our residuals. So graphing those, we have 0 and negative 13. So notice I don't have enough to get to negative 13. So let's make this 2, 4, 6, 8, 10, and 12. And then, actually, that doesn't work either, so let's do 3s. 3, 6, 9, 12, 15. So this would be negative 3, negative 6, negative 12, and negative 15. So when I graph them, I have 0 and negative 13. So 0, negative 13 would be about here. Then 2 and 0. I'm just going to keep my x-axis the same. Then 4 and 9. 6 and 11, which is a little bit under 12. 8 and 7. 10 and 1, negative 1. And 12 and negative 11. So above it says sketch a scatter plot, or sketch the plot of the residuals below. Do the residuals show any distinct pattern? And yes, this definitely does have a pattern. Okay, it goes up and down. The points are not scattered above and below the x-axis. So on the next page, we're going to see that that means something. So generally, we do not want residuals to fall along a curve or make a distinct pattern. If so, then it is likely that a linear model is not appropriate, and it's better to fit the data to an exponential or quadratic model. So if you go back to the one that we just did, that one, if we were looking at the actual graph, if we go to zoom 9, okay, this line here doesn't really look like a best fit. Instead, something that looks like this would be better, and that would probably be better represented by an exponential function or a quadratic function. So that's the purpose of the residual. We see a pattern, therefore we know a linear model is not the best fit. Okay, so now we have a school district was attempting to correlate the number of hours a student studies in a given week with their grade point average. They surveyed 8 students and found the following data. So again, we're going to go back into our calculator. Let's go to our y equals and get rid of that equation, and then go to stat and edit and get rid of all the values here. And re-enter our new data. So for hours of studying, we have 3, 7, 2, 11, 8, 16, 5, and 9. Then for our L2 is going to be our GPA. We have 78, 80, 75, 94, 89, 92, 80, and 84. So we're going to find the equation for the line of best fit and the associated R value. Round the linear coefficients to the nearest tenth and the R value to the nearest hundredth. Then create a scatter plot with both the data and the line graphed. So again, we go to stat, we go over to calc, we go to choice 4 for lin reg, enter all the way through, and we have our equation rounded to the nearest tenth would be y equals 1.3x plus 73.7, and our R value is 0.88. Okay, so now I'm going to go to my y equals. I'm going to put that equation in. And I have, again, 1.3x plus 73.7. And again, I can go right to zoom 9 and pull up that scatter plot with the line of best fit. And this time, you can see the points are scattered above and below that line. All right, so now we're going to calculate the residuals and place them in the table with the predicted values rounded to the nearest integer and the residuals for each point, the same way we did before. So we're going to go from here. I want to pull up my predictions by going to second and table. And these give me my predictions from my line of best fit. So for 3 and 78, the prediction would have been 74, 73.7 rounded. Oh, nope, wrong one. 3 would be about 78 rather, 77.6 rounded up. So those are pretty close, actually perfect if without the rounding. Then 7 is going to be rounded to 82.8, so 83. 2, 75, so instead we're going to go to 2, and that would have been 76. 11, I have to scroll down, and that would have been 88. 8, 84. 16, 95, 80, no, sorry, 5 is 80 again, and 984, we're going to change to 85. Okay, so now we could do the residuals just by subtracting the actual minus the prediction, or we can go back to stat, go to edit, go over to L3, choose second list, and change L3 to residuals, enter, enter, and now we have the actual residuals. We're rounding those, so that 0.2 is going to stay 0. 78 minus 78 is 0. Then 80 minus 83 is going to be negative 3, which is verified in the table. 75 minus 76 is going to be negative 1. 94 minus 88 is going to be 94 minus 88 was 11, about 5. 94 minus 88, I would have said 6. So let's make that negative 6 because of our rounding is a little bit different. No, positive 6 rather. Then 89 minus 84, that one here would be 5, but because of our rounding, it looks more like 4 in the table. Then 92 minus 95 would be negative 3, which is shown in the table. And then 80 minus 80 stays at 0. And 84 minus 85, because of rounding, it looks like it should be -2. I'm going to go with -1. So if they ask you to actually do the prediction and you subtract, stick with what's in your actual table. If you're just going by the residuals, we could have rounded those other ones up according to the table values. All right, so now we're going to take those and we're going to plot them in our residual plot. So again, this remains our x values, and this is now our residuals. Our largest residual is only 5, so we don't have to change the scale. So for 3, we have a residual of 0. So 3, 0 is one of our points. For 7, we had a residual of -3. For 2, we had a residual of -1. For 11, a residual of 5. For 8, a residual of 4. Actually, I think that one was 5. So we'll put in 5, 2, 4, 6, 8, and 5. For 16, our residual was -3. For 5, our residual was 0. I feel like that was actually 1 when I did it though, so I'm going to do -1 here. And then 9, our residual was also -1, although it looks like 2 there. So 9, 2, 4, 6, 8, 9. And then -1. Okay, so here, in this case, we do not have a distinct pattern. There is no curve in our residual plot. So why does this residual plot show a more appropriate linear model than the one in problem number 1, even though the R value is worse? So here, the residual plot shows a more appropriate linear model because the points are scattered above and below the x-axis, and there is no distinct pattern in the residual plot. Okay, so the gist of today's lesson is when you're creating a residual plot, if there's a pattern, a linear model is not appropriate. If there is not a pattern and the points are scattered above and below the x-axis, then a linear model is more appropriate. Okay, so you're going to go on with the rest of the questions on your own, and I'll be coming around to help you guys out as you're working.